So let's begin then with our computation of the commutator Lx commuted with Ly. And remember, these are all operators. So we won't be writing any more operator hats. Those are the last operator hats I'll be writing down. Now, in order to compute these, we of course need to know the definitions of these operators. We can get that from the cross product definition, or we could simply remember the definition of Lz, which we can more or less remember and picture from the corresponding cross product determinant. And it takes on the value of x times py, and remember these are now operators, minus y times px. So, if I want to compute my commutator and I want to first insert Lx, notice I can get that from Lz by cyclic permutation, where again, z goes one slot forward, right, which then, because z is at the end of the line, it will become Lx, and then the rest of my formula simply follows. X moving one unit forward would be y, py, the y moving forward would give me z, minus then cycling y forward is z, and then I would then have py. Very good. So at this point, what I've done is I've written down Lx. For Ly, I can apply the same logic. To go from Lx to Ly, I'm cycling forward one unit, and so this formula should move ahead one unit to generate Ly. Y then would become z, so that becomes z. Z becomes x, so that becomes px, minus then again, z becomes x, and then py would become pz. Very good. Now, we want to expand out this compound commutator into its smaller commutator units. We've done this type of thing before, but I'll just do it a little bit slowly as we get more used to this. So remember, this here is just a unit. Think of these terms here as a unit. I then have the commutator of a sum with an operator. Well, that will always be the sum of the commutators with the operator. So I can write out these two separate terms individually. So that would then give me the first term is ypz, and that will be commuted then with this entire unit. I won't be rewriting it down, but that represents what's inside of this unit. Minus then, because it's a subtraction actually instead of a sum, but the logic is exactly the same, minus then the commutator of zpy, again with that unit. Finally, we can now insert what the unit is and break it up into its constituent parts. So the first term then will be ypz commuted with zpx. So I'll have ypz commute with zpx. And then I have ypz commuted with xpz with a minus sign. So that would be minus then. I've got the ypz is then being commuted with the xpz, so that commutes with xpz. Moving along to the next set of terms, I have minus zpy commuted with this sum, so that would give me a zpy commuted with, the first term is zpx. And then finally, I have a double minus sign. I have minus zpy commuted with minus xpz, so that becomes a plus. And the terms are, again, zpy, and that then is commuted with xpz as the final set of terms. Very good. Now, once we've done something like that, what I'm hoping you will notice is that this expansion is almost exactly like expanding out a typical algebraic product, a plus b times c plus d. You simply have to find all the corresponding terms and take their products. Well, it's the same. It works in the same way with commutators, except instead of just simple products, you end up with these kinds of commutators. Very good. So let's now consider the individual commutators. Some of these have a very interesting structure. For example, let's look at this first one. Let's look at this one first. You will notice the interesting fact that each of these terms in here, all of them, commute actually with all of the others. These are all mutually commutative. For example, x and y are just multiplication by the corresponding coordinates, and x times y certainly equals y times x. Also, pz commutes with itself. Any operator commutes with itself. Pz acting on pz minus pz acting on pz, of course, would just give me 0. The final combination is when these coordinates are commuted with pz. But remember, the momentum in the z direction is an operator, which involves h bar on I times the partial derivative with respect to z. But by the very definition of a partial derivative, during those differentiations, we are supposed to treat the other coordinates, x and y, as constants. And derivatives commute with constants because you can always pull a constant out of a derivative. So all of these terms commute with each other. Now, when we compute this overall commutator, what we are going to do is we're going to write down all these terms in a certain order and then subtract off those terms written down in a different order. But all I'm going to do then is take the terms that are written in the different order, shuffle them around as I can because they commute, until they are in exactly the same order as the first piece, and then I'm subtracting the same thing from itself. Therefore, this term gives a net zero commutator. Now there's another term in here that has that exact same structure, and we can see that over here. Again, z, of course, will commute with itself. Py and px are partial derivatives with respect to x or y. Those partial derivatives will commute with any coordinate, such as z, any coordinate, namely, that's different from itself. And then finally, px and py commute with each other, because famously, px would be the derivative with respect to x, and py has a derivative with respect to y, but partial derivatives famously don't care the order in which we take them, we get the same thing. So all of these terms in here are all mutually commuting, and therefore the overall commutator, once again, will be 0. That leaves us then with the first and last term. Now for the first term, we do have a lot of mutual commutation going on. The one problem is that pz does not commute with z, because now we're taking a derivative with respect to the same variable that my coordinate z would happen to be. On the other hand, px certainly commutes with pz. Those are just mixed partial derivatives. Px also commutes with z, so I could commute those two because z is a different constant than different coordinate than my derivative. And finally, y also will commute with z and px. So what I will end up doing then is I will take these two coordinates that commute with everything else in my expression, and when I write down this commutator first in one order and then subtract it from it written down in the other order, what I'm going to do is to take these two parts, y and px, which commute with all of the other observables, and I'm going to commute them to the front of the expression, to the beginning of the expression, and then I'm going to factor them out. So I'm going to have a y times px. And I can do that, of course, for both the original order of the commutator and the second order for the commutator. In both cases, I can pull ypx out to the front, so I will open up a parentheses. The first term then that I end up with, then when I've done that, would have been pz with z after it, and I've moved my px, of course, to the front as I've shown you. And then I will have subtracted the thing in the other order, and that will give me a minus z pz times these same two factors that I factored out. Well, the pz times z minus z applied to pz is, of course, nothing other than the commutator between pz and z. The last term over here, I can perform exactly the same maneuver. Once again, it's this z and pz that are causing the trouble. Py and x most certainly commute with everything in here and also with themselves. So I will factor those out to the front, and that will leave me then with a plus. I can pull out again the x and the py, so it's going to be xpy. And then what I'm left with, and notice I've switched their order, but that's fine because x and py commute with each other. The main pieces that get stuck inside that I can't commute is first I'll have z and then pz in that order, and then I will have the subtraction of them occurring in the opposite order. So this then would become a commutator like so. So this is now significantly simplified. We can go yet further because we should know what this commutator actually is. You will recall that pz is just h bar on I times the partial derivative with respect to z, and that then has to be commuted with z. I can always pull a constant out of my commutator, so the overall term has then the commutator of the derivative with respect to z with z times h bar on I. And this commutator of a derivative with the corresponding variable we've used many times before, and that will just be the number 1. So this net commutator is simply h bar on I. This commutator is, notice, it's the exact opposite order from the first commutator, so this will have the opposite sign. So this commutator has value minus h bar on I, like so. Okay, finally I think we can factor out our terms. So recall that minus 1 over I is just plus I. So this whole term is really I h bar. So let me factor out my I h bar. What I'm left with then is this I h bar term times xpy. Now this term, when I bring I into the numerator, 1 over I is minus I. So I'll have minus I h bar. I factored out an h bar, so I just need a minus sign. And then what's left is this ypx. Very interesting. Because if you look closely at this, we should recognize this combination of operators. It is, in fact, nothing other than the definition of LZ. So the final result then, this is going to be the LZ operator, is that the commutator of LX with LY is a nice, simple expression. It's just plus IH bar times LZ. And oh, I broke down and I wrote my hats. I'm really not supposed to be writing the hats, but there you have them. Okay, now we can do two key things with this. The first thing is now we are prepared to complete our original expression. We were trying to compute this commutator for the express purpose of completing my expression here. We've just learned that, in fact, this commutator has the value of I h bar L hat Z. So this allows me then to write down a clean operator expression then for L hat squared. It's going to be L hat with a minus or a plus times L hat with a plus or a minus. Now notice, for the upper choice of sign, I have minus I times I, which is plus I. So I'm going to have plus for the upper choice of signs. Minus I times I is plus 1, so I'll have just a plus, then it's h bar L hat Z. If I had the lower sign, of course, it will be opposite. I'll have plus I times I, which is just minus 1, so that would give me a minus. Then I have h bar LZ, and don't forget then there's also the L hat Z squared operator at the end of the expression. And so I'm going to put a box on this because this is our final completed factorization for L squared. Very good. That's the first thing that we can do with this. The last thing that we should do while we are at it is to realize now I can compute a whole series of these commutators, in fact all of the possible commutators of L with L, by again simply applying my relabeling of the axes and cycling things in the forward direction. So x then would go to y, so this would become Ly under a new labeling. Ly then would cycle to Lz under a consistent new right-handed relabeling, must equal I h bar, and z of course cycles to the front, back, it's at the end of the row, so it cycles back to the front. That becomes L hat x. And we can do it again. Cycling forward, we would have L hat y becomes z, commuted with then z becomes x. And then finally, I have I h bar, and Lx then would become L hat z. So let's put a box around these, because at this point, I now have an interesting piece of algebra that I've got a set of operators here. And when I commute them among each other, and I compute all those possible commutators, I just end up with other members of that same set. This makes these angular momentum operators what are known as the generator of a Lie algebra. That's sort of the fancy way of putting it. The more direct way is, well, now we can calculate practically any commutator that might be of interest to us that involves the L's by simply using these identities.